We are recording this presentation, so it will be available on our website, and I'll give you those details at the end here. But I'd like to start just by introducing myself. I'm Daniel Lyon, one of the engineers at Hawkridge Systems, and we're going to be taking a look at how to program a 4-axis part, and a few different ways actually in this case. So we've also got my colleague Lindsay Widmeyer on the phone here. So she's actually going to be taking questions. If you use the GoToWebinar pane, there's a questions section in that pane. If you just send any questions that you have in that pane, then we can always get a response. And then if I see any of them pop up, I'll try and answer them during the course of the webinar. But if not, then we can always answer the questions at the end of it. So we're going to take a look at actually dealing with the positioning, wrap features, and the 4-axis simultaneous here. So essentially looking at the different options on how to see a 4-axis part there. And the first one was positioning the actual part and indexing between the different setups here. So I was just basically going through and putting in a couple of operations here, just using 2.5-axis features on my shaft. Here using the regular 2.5-axis slot feature, going and using generate operation plan to get some toolpath in here, and some toolpath on this particular orientation as well here. And the way we actually control the indexing between these is using the machine limits. So we set the machine limits up in the machine tab up here. So we go into our setup option and say we're using 4-axis, and then I set my rotor axis limits here. Now what this is going to control is actually the different solutions available. So if I need to go, say, from 0 degrees to 180 degrees, how do I get there? Do I go a counterclockwise move or a clockwise move? And if I set these up to say, I don't know, minus 90, plus 90, it's going to allow me and control the actual indexing solutions available in my option here. So I actually use maybe some of the faces over here to actually control the orientation. Once you set that indexing angles up, you have to just tell it which way to actually rotate. And basically a 0-degree position here. Now the actual solutions, how it gets from A to B, is actually controlled in the setup itself. So if we just double click on this particular setup right here, under the indexing tab, this is where the different solutions are actually going to be read out. So it depends on where my actual current position is. So this is going to be giving me the relative angle. So if I'm going between 0 and 90, it's going to give me a relative angle of 90 degrees, but it could already be at that position, or it could be at a minus 270 position. It's going to give me basically the total angle here, basically absolute and incremental angles right here. And those machine limits that we set will actually filter out the different options down here. You might get a list of, say, 8, 10, 12 different solutions to get between the different setups. But by using the options set in the machine, it's actually going to reduce the number of these parameters and options for you. And then you hit select, and that will control your indexing for you. But what about actually using, say, wrap features? If we just go back to the PowerPoint right here, well, essentially what the wrap features do is they use exactly the same 2.5-axis operations. So you're using the rough mill and the finish mill that you would set up to machine, say, the slots. The way they actually work is they use a thing called axis substitution. So in this case, if we're rotating about the X direction on our machine, we would set that up to be our rotary axis. And then what it does is it switches the Y moves out to be, rather than a linear move, it actually switches it to be a rotary move. Now, the tool in this case will always point to the rotary axis. That's one of the limitations of the actual wrap feature. It can't be off-center. But there are also some options where we need to actually define, to get the options up, we need to define a coordinate system, and we need to set the indexing parameters like I just showed you. So how would we go actually about doing that itself? Well, the first thing we need to do is we need to put in a coordinate system. I've just put in a coordinate system in SolidWorks for the end of my shaft right here. But I need to tell CAMWorks where that coordinate system is. So I go back into the machine, go back to my setup tab, And rather than using the rotary axis from a particular face, it needs an actual axis and a coordinate system defined. So that coordinate system is actually selected right here. And as soon as we select that coordinate system, rather than using the face to define it, we can actually use the axes to define it here. And by defining the x-axis, it knows to switch the y-axis to the rotary move. And as soon as I set this parameters up, the coordinate system here, the rotary axes, and the indexing at the top here, when I actually go back to my feature tree and right-click on it, you'll actually see the extra option down here for the new wrapped feature. So that option will actually only ever come in once you've actually got the coordinate system defined and those indexing parameters set up. And then it's really a case of going in and defining what type of feature it is, just like we do in the 2.5 axis. We choose our feature type at the top here. So in this case, it's a pocket, but it could be a boss that you're machining around, maybe like a tab that's sticking out. Even a slot, if you've got maybe like sometimes you see it on the gear selectors for a gearbox, for instance. If you've got a wrapped slot, you can do those as well in here. Open profile, so if you've got maybe a curve that you want the tool to follow, you could always drive it off of like an open-ended sketch geometry or something like that. Or you can even do the engraving in here as well. We'll just use the wrap pocket option, and we define our profile and end conditions down here. So in this case, I'm going to use my profile to be the actual bottom face here, and use my end condition to be the upper face right here. And our strategy is still the rough and finish. And notice that's still going to be and generate the same operations that we have in our 2.5 axis. You see exactly the same parameters. We just need to go and maybe change our tool size down to something more appropriate in here. And we also, it actually warns us here that we need to use the fixture coordinate system in the setup. So to actually get this to generate, I need to leave this. I'll change that tool. And I need to actually define it in my mill part setup up here to be fixture coordinate system, because it needs to know to rotate around that particular x-axis right here. And as soon as we do that, we can now generate our toolpath and get our wrapped pocket in there. And you'll be able to see those in the simulation. So if we just simulate this, you should see, if we slow it down right here, it's actually rotating the actual geometry there. So we can see a good idea of what that toolpath will be looking like, seeing what the finish will look like in here as well. So you can see down here, check on the geometry here, make sure it looks pretty close. Now, we do have some material left over here, and one of the biggest questions I always face is, how do I get it so I can actually remove that material out? Well, a lot of the time it's actually dependent on the actual geometry used to create the actual toolpath. And it really varies depending on if it can be actually machined or not, whether the actual designer of the actual part put that pocket in a way that actually can actually be machined. There is actually a support article on our website that I can point you to that goes into some different options on how to create it, the geometry in SolidWorks, and how you can program it in CAMWorks as well, and the differences. And I'll point you towards that at the end of the webinar there. But I suspect one of the main pieces of interest in here is how we can go about creating full 4-axis simultaneous toolpath. So for quick and easy options, I really like using the wrap features for this sort of stuff. But for more complicated geometry, like the actual gear teeth down here, I was going to show you how you might actually rough these out in 4-axis, and then maybe do a quick finish pass on them as well. So how do we start using that? Well, we'll just switch to our PowerPoint again and see some of the actual benefits. Now, using basically a multi-axis operation, and we restrict it from maybe 5 to 4-axis, tell it where the rotary axis is. Now, this one can be rotated offset from the center. You can always point it to the rotary axis, but if you've got some geometry where you need to actually pull the toolpath off the actual center axis, off the x-axis there, we can actually do that with this particular operation. We couldn't do that in the wrap feature. Now, we also get better toolpath control because we're using the multi-axis operation. There's a lot of settings that we can actually use to control exactly what we want, but that obviously makes it a little bit more difficult to program. So let's take a look at actually creating that geometry. So we go in, we use our multi-surface feature this time, and I'm just using one of my default strategies here. I'm going to use say the 5-axis strategy, and we'll use the faces to define a boundary for the actual toolpath to rough between. So in this case, I'm just going to use the 2 side walls here, and that's going to set the left-hand limit and the right-hand limit of where the toolpath will generate between. We'll generate our operation plan. We'll get our multi-axis mill here, excuse me, and then we'll go and set up some parameters. So first thing I like to always do, make sure my tool size is going to be something appropriate towards the geometry. Now we've got a small radius down at the bottom here, so we are working in metric in this case, but we could just switch all our tools in here. If we had a certain tool size that we wanted in imperial, maybe it was like 1/4 of an inch, we can actually just type that in here, and it will actually convert all those over forwards. But as far as the actual patterning goes, if we're going to rough this out, I typically use the flow line between surfaces for this particular one here, and we define those using upper and lower geometry. So we're using basically the top to bottom approach. So we're just driving the toolpath from the upper face here down to the bottom face, and we'll just create some features that represent, say, the upper pieces of geometry here. And I'll also go and create the lower ones here while I've also got this tool open. So this is the upper edge surfaces, so we want to use the first one. We'll click OK, and then we'll define our lower edge surface as the second one. The bottom radius is down here. We can always go in and set our step over as well, so maybe we'll just use a smaller step over since the geometry is quite small here. We'll go in and set our sensor allowance. Since we're doing some roughing here, we'll set an allowance here of maybe 1 millimeter to clear up on the finished pass. And we'll go into our entry and retract. Now this is one of the important ones, particularly for your rotary stuff. We'll go and use a cylinder, and in this case we're going to go about X, since our coordinate system's down here. And we'll set up our radius value here for the actual clearance plane. Now by doing this, if for instance my toolpath finishes and it finishes down, say, here, what it's going to do is it's actually going to do a radial move away to the clearance plane and then retract up. If we, say, use plane in X or plane in Z, for instance, then what happens is it might just retract straight through our part. So by using the cylinder about X, it will actually do a radial move first to make sure it can actually clear that distance and then retract up. We'll also go in and set our axis control. So this is where we really define how many axes we're using. In this case, we'll use a 4th axis. And we need to tell it in here which is the rotary axis as well. So we need to go in and say this is our rotary about our X. So if we're setting this up parallel to the X direction on our table, that's where our typical rotary axis might be. This is where we'd go and define that. And I could check to point it to rotary axis, which would do essentially the same as the rat feature, and point the tool axis always down to that central X-axis. But in this case, because the geometry might be offset a little bit, I'm just going to use some of the side tilt options down here. I'm going to set it to maybe like an 80-degree side tilt. So it's going to actually take the tool. We're just looking at this, say the spindle's coming down here. It's going to be 80 degrees off of the actual surface normal. So that's basically driving it to use the side of the tool to come down here and cut this and swath cut it. So, and we'll see what we've got there. We'll just use those settings and generate some toolpaths, see what we get, see what we end up with, and then we'll start going in and defining how to actually rough it out. So it looks like it just generated there for me. Now it looks like we've also got some lead-ins, so I might just go into my links tab up here, and some of my default settings here are set to use a lead-in on every single pass here, so we'll just remove some of those. To preview, just update, make sure we get these disappeared from it. So that clears up the end options right here. So that's almost like a finished pass apart from our allowance. But this is essentially the way the area roughing tool works. Now, one thing we might want to do actually as well is extend the toolpath a little bit further past just to make sure we clean out this material down here. So we can just use our Finish tab and our Extend Trim to go and do that for us here. So if I just put in a positive value in here, we're going to add some extension to our either end of our passes there. So that's how we can just make sure and just tweak it so it actually extends a little bit further past here. Now, we actually want to go and clear out the area in between. And the way we do that is we use the area roughing options here. So in our roughing tab, we check on the area roughing option and then use the 3 dots here. Now, this is primarily built for the impellers, but if you're using the same sort of procedure, you can do really kind of any sort of geometry. We'll go in and tell it to calculate after the gouge checking. So essentially, if you see here, if we calculate it before the tilting, that means we could potentially gouge the sidewall here. So typically we use this after gouge checking. And it also needs to know the rotary axis in here as well. So in this case, we're using the X direction. Now, one thing that was confusing when I first started using this was, why do I have a step over here and a step over in the pattern tab? Well, the step over here is actually calculating the passes in the rotary direction. The step over in the pattern tab is actually, in this case, calculating the steps down. So the step over this way is actually being calculated in the pattern tab, and the max step over here is actually calculating the step over in the kind of the XY plane, if you imagine a pocket. We'll also trim a little bit away from the end of the edges here. So this option right here, the trim cuts, basically takes a small percentage of the toolpath away from the edges. Anytime you're approaching any of the boundaries, that's usually when you'll start to get some kind of weird kind of loops or something like that. So we're just going to leave it at the default setting here, 2%, just to cut that away. But this is one check that we might want to do, is we might need to apply the actual gouge checking to this toolpath here. So we'll go in and set some gouge checking parameters up. And first thing I want to do and make sure is check link motions for collision. Now, what that's going to do is anytime we come down here and do like a link move between this particular pass and this pass, it's going to also check for the gouging in there. Sometimes what you might see is if that's off, it might actually lay the tool over and start just gouging into the actual side here. So to always make sure that that's on. And we'll go and define some gouge checking parameters here. So we'll use our, maybe we're not too worried about the holder in this case. Maybe we'll set our tool protrusion in our holder tab and we're way clear of where that tool is. Going to hit the top of the blade, the gear teeth here. So we're not too worried about that. Try and limit the selections here because this is obviously going to affect the actual calculation time. I'm going to go and add a feature to say I want to gouge check all of these surfaces in here. So one thing I do like to do is just actually make sure I'll switch my tab up here and make sure I'm actually programming the right blade. These can often be a problem if you're using a few different ones here. So it looks like that's the correct ones. So we'll gouge check those. We'll enable our options here. And then I want to tilt it away as well. So I want to use some tilt control rather than kind of moving the tool away in like an XY linear move. I want to make sure the actual tool tilts away with a rotary move. So I'm just going to use some of the lead, lag, and side tilt angles now. Now, because we're actually using the fourth axis and these lead, lag, and side tilt angles aren't relative to the actual rotary, it's relative to the surface. So my lead, lag, side tilt, my side tilt is going to be in this direction here. My lead lag is going to be along the actual tooth profile here. And we'll see what we get there just by using that area roughing. It should actually go in now and clean that geometry out in between there. It's just going to generate my toolpath, and it should pop up once we've got it in here. So it goes in and actually cleans that material out between the blade, and that's one of the more common issues. Like a lot of the toolpath you'll see is actually finishing toolpath, but actually getting the actual material out can be somewhat of a problem. So that's basically how you use the area roughing. We drive it between two faces. These two faces right here actually control the limits left and right. The upper surface and the lower surface down here control the actual volume. So really what we're defining with the initial feature is the lower limits, the left and right limit, and the flow line between surfaces controls the upper limit, so generating toolpath between the top and the bottom here, which defines really the volume in which to generate the toolpath. Now, one of the things that we might be concerned about is, well, how does it link between the different passes? If we look, it's a bit difficult to see, but if we look down in here, you may see some links that basically a direct pass. Looks like here, for instance, maybe from the end of this pass at this point all the way over down to here. As soon as you use any of these area roughing options, you'll actually get the ability to change these links between passes. So as it finishes the first step down, we don't want to do a direct move to the next position, the start point for the next pass, because that will gouge basically as it's going in and potentially break our tool. So what we might want to do is go in here and actually set it to do a clearance move, so it does a radial retract out, goes across to the start position, and then drops back in again. And you'll see as soon as I actually switch those out and hit preview again, we'll now see more rapid moves come up. So it's just regenerating there. You can see the rapid moves actually in that image on my my PowerPoint there between them. And it's that setting that drives the tool to basically pull out when it's finished this particular pass, do a radial move, come back down, drop back in again, and then we don't end up with a direct move between here and here, which would basically gouge straight through some leftover material here. And we can simulate that, see what it looks like. Obviously a pretty small tool in this case. Maybe you would probably want to reduce that tool length a little bit, but now it's going to do almost like a pocket out move on that, and we'll do our steps down. So you can see there, that's the extra, that's the step over in the pattern tab driving that depth down here. And this step over is controlled by the one in the roughing option. So you'll see there's a lot more settings to control in the multi-axis operation, but you can get much finer control. You can take the tool away from the central axis there. You don't have to point it right down to the rotary. And then as far as the finishing path goes, we can actually just copy that particular operation, the roughing operation, maybe just remove some of the parameters away and then regenerate it using without the roughing options. So if we just go back in, we'll click OK and define that. No need to regenerate since we've already got it. Fastest way I think of creating the finishing pass is basically just control drag what you had, bring it down beneath it, go back in, and then redefine some of the parameters here. So we'll maybe use the same tool, minimize some tool changes in here. We'll use the same pattern type, basically, but we might want to go in and remove the allowance here. So we're actually driving the toolpath to be created actually on the surface. And we also want to remove those area roughing options. Hit preview, and we should end up with some gouge checked toolpath. It should also be generating as if it was right on the surface, and it's basically our finished pass here. So it should just switch back once it's finished generating. So we've got a few crazy link moves here, probably because some of these, maybe the Gauss check was doing this, so maybe we want to actually go through and maybe set some of these to clearance planes, but we can just change some of the parameters in here. Tell it to retract. It looks like there's a question right in here. Let me just see what this question is. How do we control in the simulation if the tool tilts or the part rotates? Good question. So in the simulation options, if you wanted to simulate this right now, this is where we go and define it. In the motion control fourth axis, where it says to rotate stock or rotate tool, these settings are only going to be appropriate for the indexing or the positioning side of it. If I switched it out here to actually rotate tool or rotate stock in the multi-axis operation, it's not going to actually change it. So these are only applicable to the 2.5 axis index positioned stuff. If I switch it to rotate tool, you'll still see in the multi-axis operation, it's still going to do this. That's really where the machine simulation actually would come into play. That's where you can actually get a much better idea, particularly if you're doing more of this stuff. It's much clearer because you can actually set it up to rotate. You can check out all your clearances. If you're going to crash potentially somewhere, that's where you can actually do it in the machine simulation. If I just show you the first four here, for the wrap pockets, for instance, see the tool's now rotating as opposed to the stock. If I switch this out to rotate stock, the stock now rotates as if you're using it on a rotary table in a mill. Does that answer your question, Boyd? Perfect. And you can see there's a lot of parameters in here. I just used one of the default 5-axis strategies. We went in, we changed the pattern type in here, flow line between surfaces, using the upper, from the upper surface here to drive between the lower, using the edges and the radiuses down here. One thing that I like to use as well is, say for instance you're getting weird looking toolpath at the top here, maybe it starts doing some crazy loops around at the top up here. What you can use is actually just adjust this down here to say start and end at exact surface edges. And rather than actually generating the toolpath half a step over away, that's what the avoid cuts does. This distance right here is half a step over. Rather than generating there, we actually tell it to drive at the surface edge. Now this normally would cause you a lot of issues because sometimes your toolpath might not actually come and jump on the surface. It might jump on and off the surface here, causing a lot of link moves. That's where you can actually use the margins. But those margin settings down here actually only apply when you use the start and end at exact surface edges. You'll see if I avoid cuts at exact edges, those options are grayed out. So these are basically controlling where it actually generates. So if I want to pull the toolpath away from this particular edge at the top here, I would go in and say, maybe give it an edge margin. I could set maybe like a millimeter up here, and then it's going to be a millimeter from either edge, the top edge here and the bottom edge. Or if I wanted to say, hey, I just want to generate it just at away from the top edge here, maybe it's causing some weird looping, just put in a millimeter right here, and it will actually go and control it and pull that tool away from the actual edge there. Typically, just by adjusting these to something a little bit further away, you can actually create a lot less of a headache for you. You'll minimize any odd link moves and stuff like that going between the passes. So that's one of the handy options that I like to use in here, just using the start and end at exact surface edges, and then basically driving the toolpath away just slightly from the edges. If I need to pull it further away from the end here, because my toolpath's coming along here, I use my extend trim from my finish tab right here. And if we just switch back to our PowerPoint here, I just like giving you an overview of what specs my machines are actually running. That was the main content kind of dealt with for the webinar here. But I like to give you a good idea of what machine I'm running so you guys can see if your machines are similar or if you're experiencing slow toolpath generation or some weird issues, you can see what's going on. So I'm using the HP EliteBook 8570W, Windows 7, not jumped to Windows 8 just yet. I'm using one of the i7 chips and 8 gigs of RAM, so it's not a crazy amount of RAM in here, not a crazy chip speed either, but it seems to do pretty well for a lot of the different options that I come across. So one of the main ones that you face often is the graphics card. It is well worth the extra bit of cash for the workstation graphics card, and I'm running one of the NVIDIA Quadro K1000Ms. It's a 2 gigabyte graphics card. But if you're just using one of the workstation, the entry-level workstation graphics card, you'll find a lot less headaches when you're generating your toolpath or whatever. So, and then I'm running the 2014 version of SolidWorks and a 2014 SP 2.1, I think it is, for CAMWorks 64-bit. So the presentation has been recorded. I apologize for that mistake at the beginning, not being able to see my screen. But it will be recorded. It will be put up on the website so you can go back and review the steps that I took to generate some of the options there. And if you've got any questions, now's a good time to start answering them or asking them. So, and we'll sit here for a while and take any questions that you've got.